Bill Nye, the science guy, he has been getting us pumped about the final frontier and all its mysteries for decades.
We were certain that the James Webb Space Telescope would transform our knowledge of the cosmos when it launched on Christmas Day 2021, and this amazing spacecraft has not let us down. James Webb has provided astronomers with fresh challenges to tackle and inquiries to ponder since its initial observations. Our world-class observatory has fundamentally challenged our understanding of everything from early galaxy ideas to the universe's expansion, generating fears that the early universe's history may need to be revised. Bill Nye, the CEO of the Planetary Society, has spoken out about the most astounding findings made by James Webb and provided a fantastic description of how the telescope challenges our preconceived notions about the nature of the cosmos. Everything would alter as a result. Both of our perspectives on life would shift. Come explore in depth how James Webb shattering our universe. First, luminous galaxies during cosmic dawn. Astronomers believed that before James Webb, galaxies were only little clouds of gas, dust, and stars that eventually developed into the island universes we see today. However, the telescope can see infrared light, which enables it to see deeper into space and, consequently, further back in time to the formation of galaxies. You wouldn't notice any of these things if you could somehow be there staring out of your spacesuit. Although the photo was shot at infrared wavelengths, James Webb's keen eyes have discovered numerous massive, far-off galaxies that shouldn't be there. Nobody knew they were there, nobody expected them, and nobody can now explain how they had developed. Astronomers are having a hard time finding galaxies that are almost as large as the Milky Way and packed with mature red stars in deep-field photos taken by James Webb during its initial observation campaign. These galaxies are so far away that, even with the powerful telescope, they only show as small reddish dots, as revealed in a recent research based on Webb's initial data release. Astronomers determined that they were witnessing these galaxies in the early stages of our universe, about 500 million years after the Big Bang, by examining the light that these galaxies emitted. The galaxy JD1's GSZ 1410, which dates to only 300 million years after the Big Bang, is its most recent finding. It is the oldest galaxy that has ever been seen. Astronomers use an object's redshift value to determine its distance, such as in the case of JD1's GSZ 1410. The wavelength of light waves is extended as they travel through space due to the universe's expansion. Since it shifts light toward the infrared portion of the electromagnetic spectrum, this process is referred to as redshift. A source of light must travel farther and faster to reach us, and its redshift increases with distance from the source. Bill Nye said that James Webb's gear is built to study the highly redshifted light from far-off galaxies, and that light's sensitivity has allowed it to break record after record for the farthest object ever viewed. All of these things are detectable by this apparatus in the infrared, and we, on Earth, take the data and convert it to visible light. For example, the redshift value of 14.32% for JD1's GSZ 1410 poses a difficulty. Because of how weak their light is, it is sometimes impossible to gather enough data on them to make any firm judgments about their characteristics. Astronomers were first drawn to JD1's GSZ 1410 because it seemed to resist this pattern. It was a very brilliant galaxy at this high redshift. At first, it was thought that its brightness resulted from its closeness to another nearby galaxy in the sky. But it wasn't long before it was evident that JD1's GSZ 1410 was unique and had its own stunning brilliance. Because of this, it was a good candidate for further investigation, and Webb's near-infrared camera was directed on it for 5 days straight in October of last year. Scientists were able to closely investigate the composition and development of the galaxy by closely examining its spectral signature, thanks to the data obtained from this near observation. Results presented in a second publication indicate that stars with a significant star formation burst in the last few million years may have included 500 million solar masses in JD1's GSZ 1410. This occurs significantly sooner than pre-James Webb models were thought to be able to. Though it is astounding that the universe could create a galaxy of that size in just 300 million years, the Webb telescope has consistently yielded these kinds of astounding discoveries, revolutionizing our knowledge of how and when the first galaxies formed from the primordial gas released during the Big Bang. To be exact, in the first 18 months of Webb's operation, we have increased our reach 40% into the cosmic past. Scientists are further surprised by the presence of bright galaxies like JD1's GSZ 1410 in the early cosmos. This galaxy and other objects of a similar nature have great promise for future research because of their extraordinary brightness, which raises the exciting possibility of peering back in time to the cosmic beginning, the time when the first galaxies were created. Second, supermassive black holes in the early period. It is well knowledge that black holes expand by consuming nearby stars and gas and dust clouds, therefore it is unexpected to find supermassive black holes in the early cosmos, when they haven't had much opportunity to eat their surrounds. Black holes weighing around 1 billion solar masses and existing 800 million years after the Big Bang have been found by James Webb. An equally significant finding is that the oldest known black hole, which is more than 13 billion light-years distant, has been found by astronomers using the James Webb Space Telescope. Just 400 million years have passed since the Big Bang. The galaxy known as GNZ11, which was the oldest galaxy ever observed when it was discovered in 2016, contains a black hole in its center. However, there is still much to learn about these supermassive black holes, particularly when they are observed earlier than 1 billion years into the universe's 13.8 billion-year existence. This is due to the fact that it should take several billions of years for the ongoing black hole merging process, which is how scientists believe supermassive black holes form over time. Thus, how are these enormous holes able to survive just a billion or so years after the Big Bang? One theory is that the so-called hefty seed black holes gave them an early advantage in their formation. Scientists have gathered evidence that supermassive black holes in the early universe did, in fact, originate from heavy seeds by using James Webb to examine dim light emanating from stars in the host galaxies of 6 ancient quasars for the first time. Significantly more, the telescope has discovered even smaller supermassive black holes at even earlier ages, with masses ranging from a million to tens of millions of suns. This could provide scientists enough information to understand the evolution of these massive objects. Number 3. Dust in the early universe. All around us, dust may be seen in the form of fluffy bunnies hiding under our beds, black clouds obscuring our view of the Milky Way, and fingerprints seen in the spectra of far-off galaxies. Since most dust includes carbon, it was a relatively late element in the universe, having first been created by early stars from their first supply of hydrogen and helium. However, in a startling discovery, James Webb has found evidence of the ingredient that is the foundation of all life, carbon dust, in 10 distinct galaxies that date back as far as 1 billion years after the Big Bang. The discovery of carbon dust so soon after the Big Bang has the potential to challenge accepted notions about the universe's chemical development. Current thinking states that the first stars and galaxies should have been composed entirely of these light elements, as the early cosmos was mostly composed of hydrogen and helium with trace amounts of heavier elements. According to conventional conceptions, the nuclear furnaces found in the center of stars are where heavy elements like carbon and oxygen are formed during the chemical history of the universe. The material that the earliest stars had created was dispersed throughout the universe as they burst into supernovae, signaling the end of their nuclear fusion era. Interstellar dust incorporates this stellar stuff. The material that is left over when thick areas of this dust collapse becomes the building blocks of the stars that follow, which are subsequently richer in heavy elements and reside in similarly enriched galaxies. James Webb's discoveries, however, cast doubt on this, as some of the galaxies it observed containing carbon dust are thought to be about 10 million years old. That suggests that carbon must be created and dispersed via a process that operates on a short time period. The results represent the type of science that was not feasible prior to the July 2022 launch of the James Webb Space Telescope, which started studying the cosmos and providing data and photos. Fourth, constricting the universe tension. The cosmos is expanding, something that astronomers have understood for decades. Upon observing distant galaxies with telescopes, scientists discover that these galaxies are veering away from Earth. However, when astronomers have examined these separations, they have discovered that the cosmos is expanding faster than ever before. Cosmologists are baffled by this expansion pace and are searching for new answers because it is much quicker than the dominant theory suggests it should be. The source of this acceleration is known to scientists as dark energy. Although the exact nature and mechanism of dark energy are unknown, scientists believe that a cosmological constant, a spacetime characteristic that aids in the universe's expansion, might be able to explain some of its behavior. This constant was first discovered by Albert Einstein, who denoted it with a lambda in his general theory of relativity. When there is a cosmological constant, its energy density does not change as the universe expands. Envision a box filled with particles. The density of the particles would drop as they dispersed to fill the box as its volume increased. Occupy the whole space inside the box. Imagine the same box now, but with the particles' density remaining constant as the volume grows. The fact that the cosmological constant's energy density does not decrease with cosmic expansion defies common sense. However, this feature aids in the explanation of the universe's acceleration. As of right now, lambda CDM, which stands for cold dark matter and signifies the cosmological constant, which describes dark energy, is the prevailing hypothesis, or standard model, of cosmology. This model explains both the late-stage acceleration of the cosmos and the early-stage expansion rate. The cosmic microwave background, or CMB, is the leftover microwave radiation from the time the cosmos was hot and dense, around 300,000 years after the Big Bang. Its findings are explained by the lambda CDM in particular. Scientists developed the lambda CDM model based on observations made by the Planck spacecraft, which monitors the cosmic microwave background. Scientists are able to anticipate the value of the Hubble constant, which is a measurement of the universe's current expansion rate rather than a constant, by fitting the lambda CDM model to the cosmic microwave background. The lambda CDM model isn't flawless either. There is a discrepancy between the expansion rate reported in lambda CDM based on cosmic microwave background data and the expansion rate that has been determined by scientists through measurements of distances to galaxies. The discrepancy is referred to as the Hubble tension by astronomers. This higher number has now been established with even greater precision by James Webb. The difference between the two approaches implies that either scientists are misinterpreting some aspect of the universe's operation or they have made a number of observations that are all acting in the same way. Number 5. Extensive research on star formation. Dense clouds of gas and dust are where stars develop. Sadly, dust obscures visible light, making a large portion of the process invisible. However, James Webb can now see through dust owing to its infrared eyes, providing a unique perspective on star formation. For instance, it has uncovered hundreds of new stars that Hubble was unable to see that are hidden deep within the Eagle Nebula, M16. Moreover, the Ultimate Space Observatory revealed astounding detail in a portion of the Rho Ophiuchi cluster, which is close. Numerous newborn low-mass stars have been seen in the telescope's photos, along with the jets they release that illuminate nearby molecular hydrogen clouds. With its most recent observation, James Webb has made another breakthrough. This time, the dynamic telescope has observed aligned bipolar jets, something astronomers have long wanted to see, by peering into the center of a nearby star-forming zone. A group of researchers took turns using James Webb's highly sought-after viewing time, and they directed the infrared telescope towards the Serpens Nebula. The famed Pillars of Creation, which the Hubble Space Telescope made famous with its breathtaking image, are located in this young, neighboring star-forming area. Researchers weren't concentrating on the pillars, though. Rather, they focused on the Serpens Nebula as a natural laboratory to investigate the formation of stars and attempt to address some unanswered concerns regarding the process. After the Webb arrived, a group of US, Indian, and Taiwanese astronomers studied the area and published their findings in a paper titled "Why Are Almost All the Protostellar Outflows Align in Serpens Main?" Joel Green of the Space Science Telescope Institute is the principal author. Giant hydrogen molecular clouds collapse to generate stars. They begin as protostars, which are objects that are still gaining mass as they expand and have not yet started to fuse. A whirling accretion ring of gas from the cloud forms around the star. The gas warms up and releases light as it flows. A portion of the energy is transformed into angular momentum when the cloud collapses into a protostar, causing the nascent star to spin. A portion of the spin must be eliminated in order for the newborn star to continue gaining mass. This occurs when some of the gas from bipolar jets, also known as protostellar outflows, is released by the rotating accretion disk. They originate from the poles of the newborn star, perpendicular to the spin, and are an element of how stars control themselves as they expand. The jets are forced out of the poles by the magnetic fields around the star. However, the procedure is far more detailed, and certain doubts remain. Intermingling magnetic fields are at action when stars develop, and they typically form in clusters or groups. Serpent's Nebula is a fantastic spot to spy on some of this detail, as it is only 1,300 light-years distant. Even our most powerful telescopes were unable to see the detail until James Webb arrived, leaving astrophysicists to speculate based only on what they could see. Sixth, a dusty supernova remainder. When a star reaches the end of its life, it explodes in a spectacular explosion of light, known as a supernova. In a split second, supernovas have the power to outshine whole galaxies and release more energy into space than the Sun will in a lifetime. Additionally, they are the universe's main supplier of heavy materials. Supernovas are the biggest explosions that occur in space, according to NASA. The James Webb Space Telescope has now made a groundbreaking discovery in astronomy. It has managed to obtain comprehensive photographs of a supernova explosion, offering previously unheard-of insights into the star's life cycle. This occurrence represents a critical turning point in our comprehension of cosmic events. Earth first saw light from an exploding star only 340 years ago. Cassiopeia A, the remnant of this supernova, is currently seen as a debris disk spanning 10 light-years. Wispy tendrils of gas and the gentle light of heated dust are responsible for Cass A's breathtaking beauty in the infrared. Astronomers are intrigued by the dust because it is a fundamental component of planets and life. The majority of cosmic dust, they believe, originates from the heavy elements released by supernovas. Scientists expect that James Webb's investigations of Cass A and other supernova remnants will provide further insight into the origin of this material, even if earlier research was unable to explain the amount of it observed in early galaxies. Seventh, a massive surprise. Using James Webb, astronomers discovered something astonishing in the Orion Nebula around the end of 2023. 40 pairs of planetary mass objects were discovered by the scientists, none of them orbit a star. Jupiter mass binary objects, sometimes known as jumbos, are what they are known as. This finding clearly contradicts the ideas of planet formation and star birth. Around 1,350 light-years away from Earth, the Orion Stellar Nursery is home to a sizable collection of these bodies. It is unknown where these orbs originated or how they got to be there. Because the presence of jumbos defies widely accepted theories of planet and star formation, these objects have proven difficult to explain. Jumbos are hot, gassy, binary structures that at first glance may appear to emerge when areas of gas and dust clouds that are too thick collapse. This is the process by which stars originate, and it's also the method used by failed stars, sometimes known as brown dwarfs, who derive their moniker from the inability to fuse hydrogen to helium in their cores. But one distinguishing feature of stars is that jumbos probably enter existence via a different path. When the masses of those stars drop, the likelihood of a star having a binary partner also decreases. For instance, approximately 50% of stars with masses comparable to the Sun are discovered with a stellar partner, but about 75% of large stars are found in binary pairs. It is vanishingly unlikely to discover a brown dwarf in a binary system with a mass of around 0.75 times that of the Sun. Jumbos have masses that are fewer than 13 times that of Jupiter, which is below the lowest limit of brown dwarfs. What is happening, then? Moreover, conventional planetary formation theories also fail to explain jumbos. According to these hypotheses, they originated from gas that was left behind from a parent star or stars. Even while we are aware that planets are frequently expelled from their home systems and end up as rogue planets, or cosmic orphans, roaming the universe without a parent star, this process ought to be so intense that it shatters any potential planets that are gravitationally linked. Therefore, it appears that any unusual ejection event that resulted in a planetary pair being expelled together without being split up is ruled out by the fact that scientists discovered 40 pairs of jumbos in the Orion Nebula alone. Rethinking and improving current ideas of planet formation is made possible by our understanding of the development of jumbos. James Webb's next observations might do that, each one providing fresh information that improves our ability to develop novel hypotheses on the origin of massive planets. Eighth, a revolution in molecular exoplanet science. Despite the fact that pictures receive the most attention, spectroscopy is crucial to James Webb's investigations. It enables scientists to examine the chemical makeup of celestial objects and calculate the redshift and, consequently, distance of distant galaxies. This is especially crucial for studying the atmospheres of exoplanets, as Webb's infrared capabilities enable it to identify chemicals that are undetectable to the human eye. Because of how sensitive this telescope is, you can determine the makeup of the atmosphere. The Premier telescope has made several discoveries, one of them being the detection of putative biosignature components in the atmosphere of the exoplanet K2-18b, a super-Earth that is situated around 120 light-years away from Earth. Despite the fact that many exoplanets are harsh, violent, or at the very least alien in nature, whether they are frozen remnants at the edge of their systems, are subjected to intense radiation from their stars, or lack a solid surface, K2-18b was a tempting target in the hunt for life because of how similar it is to Earth. K2-18b has 8.6 times the mass of Earth and is 2 to 3 times wider than Earth. It is situated in the region that is neither too hot nor too cold to contain liquid water, known as the habitable zone of its star. According to this theory, the exoplanet is an ocean or oceanic world that is full of liquid water, which is essential for life as we know it on Earth. The atmosphere of this exoplanet appears to be mostly hydrogen rather than nitrogen, in contrast to Earth. The identification of carbon dioxide and methane was the main finding of the University of Cambridge scientists' use of the James Webb Space Telescope in their study of K2-18b. Since there were no ammonia traces found in these molecules, it was clear that the planet should have high pressure, with a large ocean under a hydrogen-rich atmosphere. However, there was also a glimpse of something else, something extremely exciting, the audacious hypothesis that something, potentially a life form, must be present on K2-18b if it was making it at a pace 20 times faster than that of Earth. In an interesting recent discovery, the James Webb Space Telescope has recorded the most thorough weather report from fallen stars yet, spotting stormy weather in the sky of 2 brown dwarfs. The 2 brown dwarfs were found together in 2013 by NASA's Wide Field Infrared Survey Explorer, WISE, as a binary pair known as WISE 1049ab. With only 6.5 light-years separating them from Earth, the pair is a prime target for the James Webb Space Telescope's powerful infrared detectors. Something that isn't quite large enough to start the nuclear fusion process that turns hydrogen into helium in its core and develop into a star is known as a brown dwarf. It is believed to originate similarly to stars, by the gravitational collapse of a cloud of molecular gas, but it is also too big to be a planet. Therefore, brown dwarfs are considered to be the missing piece connecting the lowest mass stars, M dwarfs, and gas giant planets like Jupiter. Prior studies have examined the atmospheres of a number of brown dwarfs, but they have always been restricted to time-averaged snapshots, making it impossible to discern how the atmosphere of a brown dwarf changes over time. Brown dwarfs do, however, rotate quickly. WISE 1049a rotates once every 7 hours, and B once every 5 hours. Since their atmosphere's characteristics might change over time, many variables might have been overlooked in observations that did not account for the object's evolutionary history. Nevertheless, these variations over time can be seen by the Webb telescope. A group headed by Beth Biller from the University of Edinburgh used James Webb's MIRI to watch WISE 1049ab for 8 hours, and then its NIR spec for an additional 7 hours just after that. The scientists discovered that both brown dwarfs are engulfed in turbulent clouds, most likely made of silicate granules, and that they are very hot, between 870 degrees Celsius and 1126 degrees Celsius. Put another way, the winds of the brown dwarfs are carrying heated sand. Additionally, the absorption signatures of water vapor, methane, and carbon monoxide were determined. A graph showing each brown dwarf's brightness with time is called a light curve, and it shows some interesting variety. This has been explained as stormy weather creating gaps between clouds that reveal glimpses into the lower levels of the sky and blowing clouds at different heights. Additionally, the light curves display maxima at certain wavelengths, methane at 3.3 microns, carbon monoxide at 2.3 and 4.2 microns, and silicate grains, maybe between 8.3 to 8.5 microns. According to Biller's team, the peaks at these wavelengths point to 3 distinct strata on each brown dwarf where there is a noticeable variation in atmospheric pressure. A high-altitude layer displays signals between 4.2 and 8.5 microns, an intermediate altitude layer absorbs light at between 2.3 and 4.2 microns, and a deep layer produces signals larger than 2.3 microns but less than 8.5 microns. The results demonstrate James Webb's ability to examine a brown dwarf's vertical atmospheric profile for the first time. In fact, as the study report summarizing the findings points out, there's no reason the Webb telescope needs to end there. Although this is the first of its kind, it won't be the last. James Webb will revolutionize our understanding of both young giant and brown dwarf exoplanet atmospheres over the course of the next several observation cycles. Rings surrounding the Ring Nebula in number 9. One of the most exquisite planetary nebulae in the sky, the Ring Nebula, also called Messier 57 in Lyra, is the last condition of Sun-like stars. About 20,000 clumps of molecular hydrogen make up the ring itself, and James Webb has disclosed minute information about it. However, a group of 10 concentric arcs that extend over the outside border of the main ring of Messier 57 are what really make the object stand out in photos taken by James Webb. Scientists believe that the arcs originated close to the dying star as a result of gas expelled from it interacting with a low-mass companion orbiting at a distance comparable to that of the Sun and Pluto. 10th, examining protoplanetary disks. In the dusty gas disks that encircle newborn stars, planets form. Webb's investigations have yielded intriguing hints of life antecedents orbiting the neighboring star fallout, in addition to providing hitherto unexplored detail in these protoplanetary disks. 3 nested bands of heated dust were discovered by the telescope, indicating that the disk was formed by planets. In the inner disk encircling PDS 70, the observatory also found water vapor, indicating that any terrestrial planets that developed there would have access to water. James Webb identified the methyl molecule in the protoplanetary disk around the young star D203506 in the Orion Nebula. This molecule is probably important for interstellar organic chemistry and the origin of life. Number 11, there may be a secret ocean on Uranus' moon. Astronomers have found that Ariel, a moon of Uranus, could be concealing a subterranean ocean of liquid water, thanks to the use of the James Webb Space Telescope. The fact that a sizable portion of Ariel's surface is coated in carbon dioxide ice may provide insight into a riddle surrounding this Uranian moon that has baffled astronomers. This is confusing because carbon dioxide transforms into gas and is lost to space at the distance that Uranus and its moons have from the Sun, 20 times further than Earth. This indicates that a method is needed to replenish the carbon dioxide ice on Ariel's surface. According to earlier beliefs, this occurs as a result of charged particles from Uranus's magnetosphere interacting with Ariel's surface. This process is known as radiolysis, which produces ionizing radiation that breaks down molecules and leaves carbon dioxide behind. Nevertheless, fresh data from James Webb indicates that Ariel's interior, possibly a hidden subterranean ocean, may be the source of this carbon dioxide rather than the exterior. Chemical elements and molecules leave unique fingerprints on spectra because they absorb and emit light at certain wavelengths. The scientists behind this finding were able to create a picture of the chemical composition of the Uranian moon by using the Webb telescope to collect Ariel's light spectra. Ariel contains some of the solar system's richest concentrations of carbon dioxide, the researchers discovered after comparing this to computerized spectra from a chemical mixture in the lab on Earth. This not only thickened the ice by an additional 10 millimeters on the side of the tidally locked Ariel that is always pointed away from Uranus, but it also made carbon monoxide deposits visible for the first time. It just shouldn't be there, according to team head Richard Cartwright of the Johns Hopkins Applied Physics Laboratory, who made this assertion. The temperature of carbon monoxide must reach 30 Kelvin, or minus 243 degrees Celsius, before it becomes stable. Since Ariel's surface is typically around 18 degrees Celsius higher than this critical temperature, carbon monoxide would need to be continually supplied. Cartwright admits that radiolysis may contribute to part of this replenishment, but new discoveries and measurements from Voyager 2's 1986 flyby of Uranus and its moons have raised doubts about the extent of the interactions underlying radiolysis. Since the orbital plane of Uranus's moons and the planet's magnetic field axis are displaced from one another by around 58 degrees, most of the carbon-oxygen molecules seen on Ariel's surface may have originated from chemical reactions in an ocean of liquid water that was locked beneath ice on the planet. That's all in this video. If you like the information, please hit like and subscribe to this channel. And be connected to this channel for more space information.